Section 5. Field Forces, Action at a Distance. Imagine a world where objects could only interact through direct physical contact. A world without gravity, magnetism, or electricity. It would be a strange and unfamiliar place, devoid of the forces that shape our universe on both the grandest and most intimate scales. Thankfully, we live in a world governed by field forces, those mysterious forces that can act over a distance, without any direct physical contact between objects. Perhaps the most familiar field force is gravity. Gravity is the force of attraction between any two objects with mass. It's what holds us to the Earth, keeps the moon in orbit around our planet, and governs the motion of galaxies across the cosmos. Gravity is a long-range force, meaning it can act over vast distances. It's also a relatively weak force, especially when compared to the other fundamental forces of nature. But despite its weakness, gravity plays a pivotal role in shaping the large-scale structure of our universe. Another familiar field force is the electric force. The electric force acts between objects with electric charge. Like charges repel each other, while opposite charges attract. The electric force is responsible for a wide range of phenomena, from the static cling of clothes to the flow of electricity through wires. It's also the force that holds atoms together, binding negatively charged electrons to the positively charged nucleus. The magnetic force is closely related to the electric force. In fact, electricity and magnetism are two sides of the same coin, a fundamental force known as electromagnetism. The magnetic force acts on moving electric charges and magnetic materials. It's what makes magnets stick to refrigerators, compasses point north, and electric motors spin. The Earth itself acts like a giant magnet, generating a magnetic field that protects us from harmful radiation from the sun. Field forces are a constant presence in our lives, even if we don't always consciously think about them. They govern the motion of celestial objects, hold atoms together, and power our homes and cities. Understanding field forces is essential for comprehending the fundamental laws of nature and appreciating the intricate workings of our universe. In the next section, we'll delve into the concept of momentum, a fundamental property of moving objects that is intimately connected to the forces acting on them. Section 6. Momentum, the power of motion. Imagine watching a bowling ball and a tennis ball rolling towards you at the same speed. Which one would you rather try to stop? Instinctively, you know the bowling ball would be much harder to stop. This is because the bowling ball has more momentum. Momentum is a measure of an object's motion, combining its mass and velocity. An object's momentum is calculated by multiplying its mass by its velocity. The heavier an object is, and the faster it's moving, the more momentum it has. Momentum is a vector quantity, meaning it has both magnitude and direction. The magnitude of momentum tells us how much oomph an object has in its motion, while the direction tells us which way it is headed. For example, a bowling ball rolling to the right with a momentum of 10 kilogram-meters per second has a different momentum than a bowling ball rolling to the left with the same speed. One of the most fundamental laws in physics is the law of conservation of momentum. This law states that the total momentum of a closed system remains constant, even if the objects within the system interact with each other. In other words, momentum cannot be created or destroyed, only transferred from one object to another. Imagine two billiard balls colliding on a pool table. Before the collision, each ball has its own momentum. During the collision, they exert forces on each other, causing their velocities and therefore their momenta to change. However, the total momentum of the system, the two balls together, remains constant. The momentum lost by one ball is gained by the other. The law of conservation of momentum is a powerful tool for analyzing collisions and explosions. It allows us to predict the velocities of objects after they interact, even if we don't know the details of the forces involved during the interaction. In the next section, we'll explore the concept of impulse, a closely related concept that describes the change in momentum of an object. Section 7. Impulse, the change agent. In the dance of motion, momentum reigns supreme, dictating an object's relentless pursuit of its current trajectory. But what happens when an external force dares to intervene, attempting to alter this momentum? Enter the concept of impulse, the agent of change in the realm of motion. Impulse, in its essence, is the measure of how much a force changes an object's momentum. It's not merely about the force itself, but rather the duration over which that force is applied. A gentle tap might exert a small force, but if sustained over an extended period, it can impart a significant impulse, gradually altering an object's momentum. Mathematically, impulse is calculated as the product of the force acting on an object and the time interval over which the force acts. Impulse equals force times time. This simple equation reveals a profound relationship. A large force acting for a short time can produce the same impulse as a small force acting for a long time. Imagine a potter molding clay on a spinning wheel. A gentle but sustained push from the potter's hand imparts a gradual impulse, shaping the clay over time. Similarly, a golfer's swing delivers a large force to the golf ball, but only for a fleeting moment of impact. Yet both actions can result in significant changes in momentum, sending the clay spinning and the golf ball soaring. The concept of impulse is particularly useful in analyzing collisions, where forces often act for very short periods. For example, during a car crash, the impact forces are enormous, but act for a very short time. By considering the impulse imparted during the crash, safety engineers can design crumple zones and airbags that extend the duration of the impact, reducing the peak force experienced by the occupants. Impulse, the unsung hero of momentum change, plays a critical role in understanding how forces shape the world around us. From the potter's delicate touch to the engineer's life-saving designs, impulse is the invisible hand guiding objects through their intricate dance of motion. In the next section, we'll delve into the fascinating world of collisions, where momentum and impulse take center stage. Section 8. Collisions, when objects collide. In the bustling metropolis of the universe, collisions are commonplace. From the subatomic realm, where particles engage in a perpetual game of billiards, to the cosmic stage, where galaxies collide in spectacular displays of celestial fireworks, collisions are the driving force behind change and evolution. But what exactly happens when objects collide? How do we predict the outcome of these encounters? The answers lie in the fundamental principles of momentum and impulse. As we've learned, momentum is a measure of an object's motion, while impulse is the change in momentum caused by a force acting over time. Collisions can be broadly classified into two types, elastic and inelastic. In an elastic collision, both momentum and kinetic energy are conserved. Imagine two billiard balls colliding perfectly head-on. They'll bounce off each other with the same combined speed they had before the collision. Kinetic energy, the energy of motion, is transferred from one ball to the other without any loss. In an inelastic collision, momentum is conserved, but kinetic energy is not. Some of the kinetic energy is transformed into other forms of energy, such as heat, sound, or deformation of the objects. Imagine a car crash. The cars will come to a stop, their initial kinetic energy dissipated as heat, sound, and the energy required to crumple the metal. The degree to which a collision is elastic or inelastic is quantified by the coefficient of restitution. A perfectly elastic collision has a coefficient of restitution of 1, while a perfectly inelastic collision has a coefficient of restitution of 0. Most real-world collisions fall somewhere in between these extremes. Understanding collisions is crucial in a wide range of fields, from designing safer cars to understanding the behavior of gases, to modeling the formation of planets. By applying the principles of momentum and impulse, we can analyze collisions and predict their outcomes, unraveling the secrets of these fundamental interactions. Section 9. Circular motion, round and round we go. From the graceful pirouette of a figure skater to the relentless orbit of planets around the sun, circular motion is a ubiquitous phenomenon in our universe. It's a mesmerizing dance of objects moving in circular paths, constantly changing direction, yet maintaining a constant speed. But what keeps these objects tethered to their circular trajectories? The answer lies in the concept of centripetal force. Centripetal force is the force that acts on an object moving in a circular path, always directed towards the center of the circle. This force is crucial because, according to Newton's first law of motion, an object in motion wants to continue moving in a straight line at a constant speed. To deviate from this straight line path and follow a circular trajectory, a force must constantly act on the object, pulling it towards the center of the circle. Imagine swinging a ball tied to a string in a horizontal circle above your head. You can feel the tension in the string, the force you're applying to keep the ball from flying off in a straight line. This tension force is the centripetal force, constantly redirecting the ball's velocity towards the center of the circle. The magnitude of the centripetal force required to keep an object moving in a circle depends on the object's mass, its speed, and the radius of the circle. A heavier object, a faster speed, or a smaller radius all require a larger centripetal force. One of the consequences of circular motion is centripetal acceleration. Even though an object moving in a circle might have a constant speed, its velocity is constantly changing because its direction is changing. This change in velocity means the object is accelerating, and this acceleration is always directed towards the center of the circle, hence the name centripetal acceleration. Circular motion is a fascinating and fundamental aspect of our universe, governing everything from the motion of electrons around an atom's nucleus to the intricate dance of galaxies within clusters. By understanding the principles of centripetal force and centripetal acceleration, we can unlock the secrets of this mesmerizing motion and appreciate the elegant physics behind these celestial ballets.